Namaskar. So, in today's lecture we will discuss about two theorems, those are reciprocity theorem and the compensation theorem. So, let us start with the reciprocity theorem. So, what does reciprocity theorem says? Basically, it is a very important aspect of reciprocity theorem that it does not hold for all networks. So, we have to be very careful when we deal with the reciprocity theorem, and we have to keep remembering the restrictions which are imposed on the reciprocity theorem, because if you do not follow, then the reciprocity theorem you will use wrongly, and that may lead to a serious erroneous result in the circuit. So, in this lecture we will explain what do we mean by reciprocity theorem, and we will also take one example to make the things clear. Now, let us see what do you mean by reciprocity theorem. The theorem says that if an EMF E, EMF is nothing but electromotive force E, in one branch of a reciprocal network produces a current, that is I, in another branch, then if the EMF is moved from first to the second branch, it will cause the same current in the first branch where EMF has been replaced by a short circuit. So, let us understand this definition with one circuit. Suppose we have originally one circuit as shown in this figure, where one voltage source E is present between node A and B, and it is causing a current I to flow in the resistance and along the node A and D. So, when this will be energized, the circuit will be energized, the current will flow in this particular branch. So, we are saying that suppose this current is I. So, what reciprocity theorem says, that if you replace, if you exchange the locations of this current and voltage source E, then the other values are not going to change in the circuit. So, what does it mean? It means that we are replacing the value of E. So, how you will replace? You will just switch the locations of both of the parameters. One is E, that is voltage source, and second is current flowing in this particular branch. So, if you place the voltage source at current location, you have to make sure that the polarity of voltage source should be in such a way that it will give power to the circuit in the same direction as the previous direction of the current was. So, that is why if you see here, between C D, the polarity of E is minus is on the top and plus is on the bottom. So, this will make sure that the current which is flowing from the source would be in the same direction as if it was there when the original circuit was energized. Now, next is that when you will place the current in that branch where voltage source was connected. So, what you have to do? You have to simply short circuit the nodes A and B, because now voltage source is not available. So, this would be short circuited and the same current will flow in the branch, keeping other parameters same. So, that means that you can exchange the locations of voltage source and the current. Now, important thing is that the reciprocity theorem can be applied only when the circuit is linear and there is no any time varying element. Now, in other words, you can also say that reciprocity theorem can be interpreted as when the places of voltage source and current in any network are interchanged, the amount or magnitude of voltage and current flowing in the circuit remains same. Now, as we discussed that polarity of voltage source should be identical with the direction of branch current in each position. So, important factor to keep in mind is that the reciprocity theorem is applicable only to a single source network. So, if there is a network where multiple sources are connected, you cannot utilize the reciprocity theorem over there. So, this is the limitation which we have to always keep in mind, otherwise we will use reciprocity theorem wrongly. Now, let us understand this aspect with the help of one example, so that you are more clear about the particular theorem. Let us see one particular circuit which is shown in this figure. We have a voltage source E, that is 45 volt, giving current as Is to the circuit, and the 4 resistances you will see in the circuit are shown. Now, we have to prove that if you exchange value of the location of I and E, the values of current I is not going to change. So, what we will do, we will first find out what would be the value of I in this particular arrangement. So, we will first try to find out the equivalent resistance of the circuit. So, the equivalent resistance of the circuit would be R equivalent, and here you will see that 2 plus 4, that is 6 ohm is in parallel with 6 ohm. So, you will get 3 ohm as a value, and this value of 3 ohm would be again in series with R1, that is 12 ohm. So, you will finally get 15 ohm, which this particular source will see into the circuit. So, now we have got 15 ohm as a total equivalent resistance of the circuit. So, you can find out the value of current Is. So, the current Is would be 3 ampere, because 45 by 15, 45 volt is the value of voltage source. So, you have got 3 ampere. Now, you can use current division rule, because here the current is being divided into 2 parts. So, the current flowing in this would be the value of resistance this divided by the sum of the resistances. So, you will see here the 3 is the current value ampere, 6 is this value of the resistance, and summation of the resistances, that is 6 plus 2 plus 4, that will become 12. So, with current division you can easily find out the value of current flowing in this 4 ohm resistance, that is I, and the value of I is 1.5 ampere. Now, to prove the reciprocity theorem, what we will do, we will interchange the locations of E and I. So, what would happen in that case? The circuit will be modified as shown in this figure, where you will see the direction of E is downward. So, the negative sign is on the top, plus sign would be on the bottom, and Is current would be flowing in this direction, which is same as the direction of I was in the previous figure, and the location where the voltage source was connected, we have short circuited, and we assume that the current I, which is same as it was in the previous case, is flowing in the short circuit leg segment of the circuit. So, now we have to prove this value of I again would be 1.5 ampere when the circuit is modified as per reciprocity theorem. So, now again if you see what would be the value of equivalent resistance, you will see here these two are in parallel. So, 12 in parallel with 6 plus the parallel arrangement would be in series with 2 ohm resistance and 4 ohm resistance. So, finally, when you will solve, you will get the value of equivalent resistance as 10 ohm. Now, in this case, what value of Is, that is source current, you have got? 45 is the value of voltage source, and the resistance which you have got seen by the source from this side, that is equivalent resistance of the circuit. So, when you calculate the value of source current, it will become 4.5 ampere. Now, by current division rule, you can again find out what would be the value of current I. So, we will follow again the current division rule, and we will say that the value of current I is again 1.5 ampere. So, you can see from here that you need to find out the value flowing in the short circuit segment. So, this would be the 12 ohm and 6 ohm. So, 12 ohm plus 6 ohm has come in the denominator, 6 ohm is the value here. So, we follow the current division rule and it will come out to be 1.5 ampere. So, we can see now in both of the cases the current I is same. So, that means that we can say that the reciprocity theorem is justified in this particular circuit. So, the circuit which is modified and we place the voltage source in such a way that it is the current coming out of the voltage source is in the same direction, and we short circuit the current I, the segment where the voltage source was connected, and we found that the value of I is same as it was there in the previous case. So, this justifies that the reciprocity theorem is applicable in this particular case. Now, let us talk about another theorem which is called as a compensation theorem. Compensation theorem is also one of the important theorems in the network analysis, which finds its application mostly in calculating the sensitivity of the electrical circuit. Sensitivity means when you change the value of voltage a little bit, say delta V, how much the current will change in that particular segment where you are trying to find out the sensitivity. So, that will give you the value of sensitivity of that particular circuit element or the particular segment in which you are trying to find out. Now, particularly what does compensation theorem means? Now, the calculation of current change delta I in a circuit may be carried out by replacing the added resistance delta R by a series combination of voltage source, that is a combination of original current I into delta R and resistance delta R, while at the same time replacing all sources in a circuit by their equivalent impedances. What does it mean? Suppose you have a network and the two terminals of the network are having the load connected, that is the value of load is RL. So, what you can do? You can replace the whole circuit as a Thevenin equivalent, that is what we discussed when we discussed the Thevenin's theorem. So, linear two terminal network can be replaced by its Thevenin equivalent. So, here we have created Thevenin equivalent of the network. Now, suppose if there is a change in value of load RL by delta R. So, what will happen in that case? The value of the updated value of the resistance, that is RL plus delta R, will cause a change in the load current. So, now earlier it was the load current as IL, it has become IL dash. So, IL dash minus IL is nothing but equal to delta I. So, what you can represent equally that if you want to see the impact of only the delta I, you can equivalently represent the circuit as the new voltage source V c, which opposes the direction of the flow of the current, and the value of V c is I into delta R, which would be connected in series with R L plus delta R. So, now the value of current flowing delta I would be the value of V c, which you will see in the voltage source, would be I into delta R. So, now you again see the compensation theorem, the calculation of current delta I. So, when you will place the arrangement like this, you can easily find out the value of delta I. So, what would be the value of delta I? Delta I would be simply V c. Here, since the direction of V c is opposite to current flow, so this will become minus of V c divided by R L plus delta R plus R T H. So, this would be the value you can simply calculate with the help of the updated circuit. So, by using the compensation theorem, you can directly see what would be the impact of delta I, impact on delta I because of the change in resistance delta R, and this is what the compensation theorem says. So, it says that calculation of current change delta I in the circuit may be carried out by replacing the added resistance delta R, that is the added resistance delta R, by a series combination of voltage source I into delta R. So, this is a voltage source I into delta R and resistance delta R. So, the resistance will be intact, the original resistance R L. So, R L plus delta R will be the updated resistance, while at the same time replacing all sources in the circuit by their equivalent impedances. So, that means that the original Thevenin voltage we are replacing with the short circuit. If we have a current source, then it will be open circuited, while keeping all resistance value in the circuit. So, equivalent resistance value of the circuit is R T H. So, that is kept in the circuit, and with this the arrangement you can easily find out the value of delta I, which is flowing into the circuit because of the value of resistance changes from R L to delta R, R L to R L plus delta R. So, this is what compensation theorem says. Now, let us understand and justify our understanding what we have discussed till now. The compensation theorem will give you the value of voltage source I delta R, that is nothing but the value V c which we have seen, and the orientation would be in such a way that it will oppose the original current. So, alternatively we can also say that the resistance of any network can be replaced by a voltage source having the same voltage as the voltage drop across the resistance which is replaced. So, if you see the change in resistance is delta R, voltage drop across delta R is nothing but I into delta R. So, that is why it is replaced with equivalent voltage source V c. So, let us now try to understand and derive whether the updated circuit which we have just calculated justifies the claim or not. So, let us assume that the load R L is connected to a DC source network, that is we have a network here and load R L is connected to that. So, when we discuss the Thevenin's theorem, we discuss that this particular circuit can be replaced by its equivalent Thevenin voltage in series with Thevenin resistance. So, this circuit can be replaced by the equivalent circuit as shown in the figure, and the load R L is connected across the terminal A B. Now, if you are calculating the value of I L, what would be the value of I L? I L would be nothing but V T H, that is our Thevenin's voltage, divided by R T H plus R L. So, current IL would be VTH divided by RTH plus RL. So, this is we have got. So, RTH is nothing but our Thevenin's resistance. Now, let us see if we change the value of load resistance from RL to RL plus delta R, then what will happen? Since the rest of the circuit remains unchanged, the Thevenin's equivalent network will remain same as shown in the next slide. So, what happens now? The other parameters of the circuits are same. So, there is no change in the Thevenin equivalent. Thevenin equivalent will remain same. The only change would be the load resistance, that is now RL plus delta R. Current now flowing through the updated load resistance is now IL dash. So, what will happen, what would be the value of IL dash now? IL dash would be VTH divided by total resistance of the circuit, that is RTH plus RL plus delta R. Now, we apply the compensation theorem and we replace the voltage source with its internal resistance and put another voltage source, that is Vc. So, now as per compensation theorem our circuit would be like this, where we are short circuiting the voltage source which is there in the network. In this case it was VTH. So, we have short circuited the voltage source VTH. Now, we have connected the voltage source Vc. The value of Vc is nothing but I into delta R. So, here the magnitude would be like this, but since it is in the opposite direction it will become negative. So, that we will see when we will finally derive the condition. So, now let us assume that the value of delta I is the change. So, delta I would be nothing but I dash minus I. I dash was the value where the updated current was flowing when delta R was added, and IL is the original current. So, here this would be the value of delta I is nothing but IL dash minus IL. Now, substituting the value of IL dash and IL in the above equation. So, this is the equation where you will put the value. Delta I is nothing but, what is IL dash? IL dash is nothing but VTH divided by RTH plus RL plus delta R. So, we have put the value for IL dash. What is the value of IL? IL was VTH upon RTH plus RL. So, that we have again put the value of IL. Now, if we simplify, so we just take the product of both denominator and use the you place this at here and this at this particular location and simplify. So, what you get? You can simply say that delta is nothing but minus has come here, because these will be nullified from here, and we get minus of delta R as a final outcome of this particular segment. Then VTH divided by the denominator, that is RTH plus RL plus delta R and RTH plus delta R. So, when you want to simplify, what you can write, delta I is nothing but minus of VTH upon RTH plus RL, because this is there in the denominator. So, you will keep VTH and RTH plus RL as together. So, we have kept VTH upon RTH plus RL together, and then rest of the elements like delta R upon RTH plus RL plus delta R. Now, this you know that VTH upon RTH plus RL is nothing but the value IL, which we basically calculated in our original circuit. So, now the left one is delta R into RTH plus RL plus delta R. Now, what you know, Vc is nothing but delta IL into delta R. So, Vc is nothing but minus of IL into delta R, because Vc is our added voltage source, which would be nothing but the original value of current into the resistance which is added into the original resistance. So, this we know, then we can simplify it further and we can say the delta I value is nothing but minus of Vc upon RTH plus RL plus delta R. So, with this we calculated that what would be the value of delta I when there is a change in value of delta R. Now, if you simply see this particular circuit and you try to analyze what would be the value of delta IL without having any previous information in hand, what you can write simply for this circuit, you can see that the value of delta I is nothing but the voltage Vc with negative sign, because it is opposite to the direction of current delta I, plus the total value of resistance of the network. So, that is RTH plus RL plus delta R. So, this you can see directly from the circuit, and this is what we have derived while taking the value of change of current, that is IL dash minus IL. So, this justifies that when you follow the compensation theorem, you can directly replace the voltage source, directly place the voltage source in series with the resistance where the change in resistance happened. In this case, it was delta R. So, the value of placed voltage source would be equal to the original current multiplied by the updated the change in resistance, that is delta R, and at the same time we have to keep all the other voltage sources in the network off. That means that we will short circuit the voltage source which are there in the circuit. So, without going into the derivation, you can simply use the change in the circuit, that is the change in delta R, and you can replace directly with the updated voltage source and find out the change in current because of change in resistance delta R. So, what you can say, the compensation theorem can basically summarize as follows, that with the change of the branch resistance, branch current changes and the change is equivalent to an ideal compensating voltage source, that is in series with the branch opposing the original current, and all other sources in the network being replaced by their internal resistances. So, that means that the internal resistance of the network is nothing but RTH. So, other sources are replaced by only the internal resistance. So, with this you can justify that the compensation theorem can be directly applied for a linear circuit by replacing a updated voltage source in series with the resistance where the change of delta R is happening, and find out the value directly, the change in the value of current directly with the help of updated circuit. So, with this we close our today's session. So, in this particular session we discussed about two theorems. So, in the next week we will start with some new topic on the course, that is our basic electrical circuit. Thank you.